Let's start the exercise questions. First question is we need to find the volume of 1 mole of an ideal gas at STP, standard temperature and pressure. So this is the first one. So we know that PV is equal to nRT and V will be RT over P. Now N is 1 mole. So it will give us 0.082 into 10 to the power into 273 over 1. So volume will be 22.38 or approximately 22.4 liters. In other units, apart from liter, it can be 22.4 into 10 to the power minus 3 meter cube. So one is in liters, one is in meter cube, because 1 liter is equal to 10 to the power minus 3 meter cube. We need to find the number of molecules of an ideal gas in a volume of 1 centimeter cube at STP. So we know that the formula is PV over RT. So let's put the values given. So it will give you, so N will be 1 over 2240. So the number of molecules will be Avogadro number into number of moles. So that is 6.022 into 10 to the power 23 into 1 over 22400. So the number of molecules will come out to be approximately 2.688 into 10 to the power 19. This many particles. Now we need to find the number of molecules in 1 centimeter cube of ideal gas at 0 degrees Celsius and at pressure of 10 to the power minus 5 millimeter of mercury. Third one. So volume 1 centimeter cube, temperature 0 degrees Celsius, pressure 10 to the power minus 5 mm of Hg. So N equal to PV over RT, which can be written like this. We can write it rho GH, where rho is the density, G is the acceleration due to gravity, H is the height. Pressure has the formula rho GH. So 1.36 into 980 into 10 to the power minus 6 into 1. 980 because we are in centimeter per second square, otherwise it would have been 9.8 meter per second square into 273. So from here N will come out to be 5.874 into 10 to the power minus 13. So this many moles. So the number of molecules, number of particles, Avogadro number into number of moles, that is 6.022 into 10 to the power 23 into 5.874 into 10 to the power minus 13. So it will give you approximately 3.538 into 10 to the power 11. So these are the number of molecules, total number of molecules. In question 4, we need to calculate the mass of 1 centimeter cube of oxygen capped at STP. Fourth one, N equal to PV over RT So after putting all values, we get 10 to the power minus 3 over 22.4. So mass can be found out by n, number of moles into the molar mass, that is 32 gram for oxygen. This is the case. So once you solve this, mass will be equal to approximately 1.428 milligram. Remember, 10 to the power minus 3 gram, or 10 to the power minus 6 kilogram. In the fifth question, equal masses of air are sealed in two vessels. One have volume V0 and other has volume 2 V0. If first vessel is maintained at 300 Kelvin, other at 600 Kelvin. So we need to find the ratio of the pressures. Again, quite straightforward. Moles are same, so let's call them N. So for first situation, this will be the case. For second situation, this will be the case, as R is constant and number of moles are same for both. So ratio over P1 over P2 equal to NR into 300 over V0 to V0 NR into 600. So P1 over P2 equal to 1 over 1, that is 1:1. In the sixth question, there is an electric bulb of volume 250 cc. It was sealed during manufacturing at a pressure of 10 to the power minus 3 mm of mercury at 27 degrees Celsius. We need to compute the number of air molecules contained in the bulb. Avogadro constant is given and density is also given. Sixth one, volume 250 cc, that is 250 into 10 to the power minus 3 meter cube. Then pressure is 10 to the power minus 3 mm, or 10 to the power minus 3 into 10 to the power minus 3 meters, and let's convert it into Pascal. So it will be 10 to the power minus 6 into 13600 into 10 Pascal. So pressure will come out to be 136 into 10 to the power minus 3 Pascal. Temperature is 27 degrees Celsius, that is 300 Kelvin. So N equal to PV over RT, 136 into 10 to the power minus 3 into 250 over 8.3 into 10 to the power 8.3 into 300 into 10 to the power minus 3. So after solving, we will get number of moles to be 136 into 250 into 10 to the power minus 6, 8.3 into 300. Now we need to find the number of molecules. So it will be Avogadro number, that is 6.022 into 10 to the power 23 into number of moles. So this will give us approximately 0.8 into 10 to the power 15 molecules are there. Seventh question, a gas cylinder has walls that can bear a maximum pressure of 1 into 10 to the power 6 pascals. It contains a gas at 8 into 10 to the power 5 pascal and 300 Kelvin. The cylinder is steadily heated gradually heated. Now, neglecting any change in volume, we need to find the temperature at which the cylinder will break. So obviously if the volume will not change, and ultimately because of the increasing pressure the cylinder will break. So P1 is given, P2 is also given, T1 is given, and T2 we need to find. P1 V1 over T1 equal to P2 V2 over T2. The volumes are same, so it can be P1 over T1 equal to P2 over T2. So ultimately we will have T2 equal to P2 into T1 over into P1. Oh, there's slight mistake here. T2 is this should be P2 and this should be P1. So 1 into 10 to the power 6 into no, it's correct. So 1 into 10 to the power 8 into 10 to the power 6, 1 into 10 to the power 6 into T1 which is 300 over P1 which is 8 into 10 to the power 5. It will give us 375 Kelvin. So T2 will be 375 Kelvin. In question 8 we have 2 gram of hydrogen sealed in a vessel of volume 0.02 meter cube and it is maintained at temperature 300 Kelvin. We need to find the pressure. Now question 8. So what do we have? Mass is 2 gram, then V is 0.02 meter cube, then T is 300 Kelvin, P is unknown, PV equal to nRT, where N is the number of moles, so N can be given mass over molar mass. So P equal to mRT over mV. So P equal to, given mass is 2 gram, R is 0.082, temperature is 300 Kelvin, then the molar mass is also again 2 gram, and the volume is equal to 20. Uh, 0.02 meter cube. So after solving this, pressure will come out to be 1.23 into 10 to the power 5 pascals. In question 9, the density of ideal gas is 1.25 into 10 to the power minus 3 at STP. We need to find the molecular weight of the gas. Ninth one. So P equal to nRT over V, or M over M RT into V. So now it is given that the density, mass upon volume is the density, so rho is the density. So density is given 1.25 into 10 to the power minus 3 gram per centimeter cube. R is 8.31 into 10 to the power 7 erg per degree per mole. Temperature is 273 Kelvin. and m is unknown. This pressure is given, which is 13.6 into 980 into 76. So from this m can be calculated. It will come out to be 0.02796 into 10 to the power 4, or approximately equal to 28 gram per mole. Now in question 10, the temperature and pressure at Shimla is given and at Kalka is also given. We need to find the ratio of the air densities. So at Shimla 15 degrees Celsius, that is 288 Kelvin. At Kalka 35 degrees Celsius, that is 308 Kelvin. At Shimla pressure is 72 centimeter, or 72 into 10 to the power minus 2 into 13600 into 9.8 Pascal. Pressure at Kalka is 76 centimeter, which will be 76 into 10 to the power minus 2 into 13600 into 9.8. So PV is equal to m over m RT. PM equal to mv RT. Density is equal to PM over so this is PM equal to rho RT. So density is equal to PM over RT. So from this, density at Shimla over density at Kalka equal to pressure at Shimla into m over RT Shimla into RT Kalka over pressure at Kalka into m. So we will have, after putting all the values, we will have 72 into 308 over 76 into 288. So this will be 1.013. Or if you want to find for this Kalka over Shimla, then it can be 1 over 1.013, which will be 0.987.